So those are the material properties we're going to need for this. Now we want to include the other given things. For the brass, it's 3 feet long, or its length is 3 feet, which is going to be 36 inches. Again, I want to be working in base units here. For customary, inches is going to be our base unit of length. And the length of the aluminum, 2 feet or 24 inches. The cross-sectional area of each member is 1.75 inches squared. And then what other piece of information do we need to include here that we will need in our equations? Right, the delta T is really the important thing. It was installed and stress-free at 50. It's now 120 degrees when we analyze it. That's a change in temperature of plus 70 degrees Fahrenheit. We want to know the stress in the brass, the stress in the aluminum, normal stress brass, normal stress aluminum, and we want to know how far will the collar be displaced. I'll call that big delta AB. All right, so looking at our diagram to see how many free body diagrams we need. The brass piece has a constant cross-section, a constant material, and there's a constant internal normal force, which in this case there's zero. There's nothing to be applied to it, so it's constant throughout. Then here the material changes, so we need another picture for that. I'm going to take everything to the right of that piece. There's no applied loads on it, but there is a load at C from the wall. And the picture looks the same for the brass piece here. But we see from the free body diagrams, I don't know the wall reaction at C. I don't know the internal force in AL. I don't know the internal force at BR. This is a statically indeterminate problem. I can't get numbers for my internal forces just from the free body diagram. And this is the beginning of the complication that starts to get added to this problem. I can still write the equations of equilibrium, though. I still know it's negative PAL minus C is equal to 0. And negative PBR minus C is also equal to 0. I'll use this fact later. I know that PAL will be equal to PBR will be equal to negative C. I don't know what the values are yet, but I can use this substitution later. In the compatibility step, well, first we're looking for how far point B displaces. We want big delta AB. Like in the previous one, point B is going to displace as much as the brass section does. However, what additional thing can we say about the compatibility here? Right, because the walls don't move, however much the brass expands, the aluminum must compress that much, or vice versa. What can we say about big delta between A and C? Right, it's 0 because the walls don't move. So the change in distance between A and C is 0. And like you just said, that's also delta AB plus delta BC. Or delta brass plus delta steel is going to be equal to 0. This is a key thing you have to realize in this compatibility. We need this equation to be able to solve it. This is going to tell us from equation 4 that delta steel is equal to negative delta brass. So we know that the deformation of one is the negative of the other one, which we'll use also. So our compatibility is done. We now have a more complicated relationship between the deformation and the internal loads. We still have the mechanical deformation, so we're still going to have PL over EA for the steel piece. Yeah, there's no steel in this one still. All right, let's start with aluminum. We have the mechanical deformation, always there, plus the thermal deformation because there's that change in temperature. We don't know what the number is for this. I'll still express it as PAL. We do know the length of the aluminum is 24 inches. The Young's modulus of the aluminum, we looked up, 10.6 million. Cross-sectional area, we were given 1.75. Plus alpha aluminum, 12.8 times 10 to the negative 6. The delta T is positive 70. The length, 24 inches. In this equation 5, there's only one unknown in it in the right-hand side, PAL, which we still don't know. For the brass section, I won't write out all of it, but it's the same idea. P brass times its length of 36 divided by its Young's modulus, 14.6 million. Same cross-section. It has a coefficient of thermal expansion of 9.8 times 70 times 36. If I look so far, I'll write the stress equations next. But if I look at the equations I have 6 equations. And if I look at my unknowns, I have PAL, I have C, PBR, delta BR, big delta AB, another delta, that's 5, and that's 6, the delta AC. So I do have at this point as many unknowns as I have equations. I probably would start solving for unknowns at this point, or I could write the rest of my equations up here now. The order doesn't really matter. But what I can do, I'll come back to the stress equations. I'll look at the solve right now. I know that delta AL is equal to negative delta BR. I have an expression for delta AL. I have an expression for delta BR. So these two things are, well, equal. The negative of this is equal to this. I have from previously that PAL and PBR are both equal to negative C. So what I can do is substitute in negative C into equation 5 and into equation 6, and put equation 5 and 6 into equation 4. PAL and PBR. They're equal to each other, and they're both negative 17.1 times 10 to the third pounds, which means they're both in compression. Going back to my stress equations, these are easy for normal stress. Just P over A, but for the right cross-section and for the right internal force here. Since I know the internal loads, I was given the area, I can find that the stress in the aluminum and the stress in the brass are both negative 9.77 times 10 to the third psi. Since I now at this point know the internal force in the aluminum and in the brass, I can now find what the deformation of the brass is up here, plugging in that information. The deformation of the brass, I get, which one is which here? For AB, I get positive 611 times 10 to the negative 6 inches.